What's up, guys? This is the work with ideal gas. So we got ideal gas that has a temperature and has a pressure, and we have the volume for it. So we only need to find the moles in the first question. So how many moles? So it's small n. So let's go PV equal nRT. Okay, and to find n, we just solve for it. So PV divided by RT. Make sure T is in Kelvin. Okay, so to change it, you just add 273.15 plus whatever is it, so T, temperature in Celsius. Okay, and then you get it in Kelvin. Cool. 2 is if the temperature is raised to 80 Celsius and the pressure is raised to 320 kPa, what's the volume? What volume does the gas now occupy, assuming no leaks? Okay. All right, so what we're gonna do is PV is gonna equal nRT. Okay, and both before and after, so when it was raised, it's only change in temperature, and the moles are staying the same. So we can say that PV, P1, V1 divided by T1 is going to equal P2, V2 divided by T2. Okay, so we're just now solving for V2. So V2 will be equal to P1, V1 divided by T1 times T2 divided by P2. Okay? Again, temperature is in Kelvin. Temperature is in Kelvin. Number 3 is the gas now has its pressure lowered from 320 kPa to 120 isothermally. Isothermally means that the temperature is staying the same. It didn't change. Okay? So we just do the same thing we did in here, but since the temperature is the same, that means we can cancel those out. So P1, V1 is going to equal to P2, V2. Sounds good. So we're looking for the volume of the gas. So V2 will be equal to P1, V1 divided by P2. Okay? 4. Calculate the work done by the gas during isothermal process. So isothermal, again, temperature is the same. Okay, so the work is equal to force times distance. Okay, and then if we divide this by A, multiply this by A, this is gonna give us a volume. This is gonna give us pressure. So can conclude that the work is also equal to the pressure times the change in volume. This is also the change in distance because it's like delta x in between. Okay, so we integrate now because the pressure changes with the volume. Okay, so what we're going to do is that work is going to be equal to the integral of P delta V. And we can call this now, so delta P dV. Okay. P is equal to nRT divided by the volume. Okay. So again, we continue. nRT 1 divided by V dV. Okay, these are constant because remember it's isothermal. So 1 divided by V, the integral of that is going to give us the natural log. So nRT natural log of, it's going from, let's go V1 to V2, so which means that V2 minus V1. No, it's actually the opposite. Natural log divided by V1. So this is the same as ln V2 minus ln V1. Okay. The R we use in the whole question is the 8.314, just to be clear. And then for number 5, the gas now compressed from the volume found in question back to its original volume 2.4. Okay. So it's going back from what you got from answer number 3. Okay, this is the change in volume now. So it got compressed. That can tell us that the work done is going to be negative on this. So it's going to be work equal P dV. Okay, this is isobaric process. Isobaric means the pressure is the same. Okay, stay the same, stay constant, which can tell us that we can take this out of the integral. So P dV, and then so this is just normal integral, P equal V2 minus V1. Okay, so this is the answer from P times the answer from number 3 minus the answer from number 1. Okay, V2 minus V1. And you get the work done, and make sure it's negative. Okay. Alright guys, if you have any questions, let me know and I'll try to help you. See you guys.